Hello again, and welcome back to another exciting segment of 600X. In the last segment, we looked at this plot. We observed that the standard deviation should always be viewed in the context of the mean, and therefore is not particularly useful for comparing the variance of sets with widely divergent means. So, for example, it doesn't tell us much about the relative variance of the absolute heads and tails differences of, say, 10 to the 8th and 10 to the 12th flips per trial. We do that using something called the coefficient of variation. What we want to do is look at the variance relative to the mean. So, not so surprisingly, the simplest way to do that is to take the variance, as shown by the standard deviation, and divide it by the mean. And that's exactly what this code implementing the coefficient of variation does. As you can see from its implementation, it's undefined when the mean is equal to 0. Well, that's the way division works. Hence, in that case, we return the special value, not a number, denoted by the string NaN. In general, distributions with the coefficient of variation less than 1 are considered low variance. Notice that if the mean is near 0, small changes in the mean lead to large, but not necessarily meaningful, changes in the coefficient of variation. Also, unlike the standard deviation, the coefficient of variation cannot be used to construct confidence intervals, something we'll talk about in the next segment. By now, you must be getting awfully bored with flipping coins. I know I am. Nevertheless, I'm going to ask you and me to look at yet one more coin flipping simulation. This simulation illustrates yet another way to use PyLab's plotting capabilities and gives us an opportunity to get a visual notion of what standard deviation means. It also gives me a chance to talk about a nicer way to structure code to do simulations. As before, FlipSim simulates a number of trials with some number of flips per trial. Flip, as before, flips a coin some number of times and returns the average heads over tails ratio. Let's go look at the code. This simulation will also give you an example of how to break up code into multiple functions when writing a simulation. Flip does exactly what it has always done. FlipSim is a bit different. Notice that it's a lot shorter than the last FlipSim we look at. And the reason is that I've got all that code to do the plotting out of FlipSim. And I've moved that into two other functions. MakePlots, and I'll come back to this in detail in a moment, makes a number of plots, in this case 2, same number of trials but a different number of flips per trial. And LabelPlot puts the usual title and labels on the plot, plus it's going to add a text box. I think we haven't done this yet. That puts some text in the plot telling us what the mean and the standard deviation are. For the moment, you can ignore some of these arguments to text, since we have to explain them shortly. Let's go to MakePlot. Well, it starts by simulating some number of flips 1 in this case, and getting a value, the mean and the standard deviation for that experiment. Then produces a kind of plot we have yet to see, a histogram. It will do it using values 1, and it will produce some number of bins, in this case 21. Let's digress for a minute now and look at how we produce a histogram. In general, the statement pylab.hist of A, where A is some sequence of values, and bins equals some number, say n, will produce a histogram with, and I'm sure this will shock you, n bins. What it essentially does is it takes the values in A and sorts them, sorts the values in A, then produces a histogram with n bins that are evenly spaced across the range defined by the minimum and maximum values in A. So for example, if we look at the code here, what it does is it starts with an empty list, puts in this case, 100,000 random numbers into that list, and then produces the histogram. When we run it, we get the following plot. Are you surprised that each bin is roughly the same height? Well, you shouldn't be, because random.random should be choosing uniformly from the space 0 to 1, so we should have about an equal number of numbers in each of these bins. Now let's add some code to the end here. This statement first invokes the function pylab.xlim, and notice that it's invoking it with no arguments. When xlim is invoked with no arguments, it returns the minimum and the maximum values on the x-axis. And then those are assigned to xmin and xmax. We'll then do the same thing with y. So we can see what those are. We're going to print these. And then, I don't know why I bothered saying pylab.figure here, since we only have one figure. We could get rid of that. Then I'm going to plot the histogram. And in fact, since I want to show you something, let me comment this line out. All right, let's run the remaining code and see what we get. We'll notice that x range goes from 0 to 1, exactly what it does in the figure, and y range from 0 to 1,000, again, as we see here in the figure. All right, now let's go back to look at the PowerPoint version of it, and let's uncomment this. Notice that here I'm calling xlim with arguments rather than with no arguments. When I do that, rather than returning the values of xlim, of xmin and xmax, it sets them. So what I'm telling it now is, irrespective of what you think the x-axis limits should be, I want -1 to be the lowest and 2 to be the largest. All right, let's run this code and see what we get. Well, it prints the same things it printed before. That's as we would have guessed. But notice how different the plot is. The y-axis still goes from 0 to 1,000, but as I instructed it, the x-axis starts at -1 and ends at 2. A lot of blank space, but not pylabs to question why. All right, let's go back to our original code here and look at what makeplots is doing. So as we said, it gets the values of the first simulation, produces the histogram. It then gets xmin and xmax, ymin and ymax, calls label plots to label the plots. And now we can go look and see what pylab.text is doing. The first arguments to it tell it where to put the text box. And here I'm telling it to put it into a location relative to the values of xmin and xmax and ymax and ymin. And then I'm telling in the box I want it to produce a string giving me the mean and the standard deviation. I then get a new figure, because we're going to want to compare two things here. Run the second experiment, again plot a histogram. Notice instead of calling xlim with no arguments to get the values, I'm going to set them to the values from the first experiment. In a minute we'll see why I did that. Then I'll get the y values, and then I'll call label plot again. All right, let's run it and see what we get. It produces these two plots. As we saw, along the x-axis, it tells us the fraction of heads, and the y-axis, the number of trials for which that was the fraction. Not surprisingly, it peaks at 0.5, half the time we got ahead. And indeed, that's the mean. Actually, this might be a little small, so let me write it larger. The mean was 0.4999, and the standard deviation was 0.0501. If we come over to this plot, where instead of doing 100 flips in each trial, we did 1,000 flips, we see that we get the same mean, actually almost the same mean. Here it actually is 0.5. Close enough to the one in the previous plot, but the standard deviation is quite different. It's 0.0158. Of course, that's exactly what we should all expect, since we know as we increase the number of flips, the variance should get smaller. In both cases, we have close to a normal distribution. The thing to notice is because the standard deviation is so much smaller, this one is a much tighter looking distribution than this one. And now you see why I went to the trouble to change the limits on the x-axis. If I had used the default, this distribution would have filled exactly the same amount of space as this, and they might not have visually looked so different. However, by forcing the axis here to match the axis here, we get the visual clue that this is indeed a much tighter distribution than this.